Okay, in this lecture I'm going to talk about a derivation of acceleration. And if this seems confusing, it's okay. What I want to do though is give you the mathematical framework for how to think about changes in velocity. Remember, velocity is a vector, which means it has a scalar component, which is the speed. This is the speed, which is again the magnitude of v. I'll just define it as speed. So this is the length of my vector times the direction that my vector is going in. So if I want to draw that, I would just say my velocity vector is this. Here's v. I know its length. I can calculate it very simply just by taking the sum of the squares of the square roots of the components. And it also has associated with it a length. This is v hat, which tells you the direction that v is going in. Okay, so those are our two quantities associated with that particular vector. So, just like we did with changes in position, we can also do the same kinds of things for changes in velocity. So my velocity can change. My vector may change direction, or my vector may get longer or shorter, or do both. It could do both. And so the way we think about this is we could say there's an average acceleration. A average. So we're going to use the letter A to denote acceleration. And that's just going to be delta V over delta T. Okay. And you might notice that the units here are actually change in velocity, which means this is length per time. So again, length per time. And there's another time. So the actual units work out to be length per time squared. And in physics, we always call this meters per seconds squared. So that's the units of acceleration, meters per second squared. Now, I can also rewrite this. A average is equal to, well, it's delta of delta r, I'm sorry, this is a vector, over delta t. So I get two changes in time. All right, so this, again, my delta r vector is in here, but then I have to think about the change in r. Right? So that will be important as we go ahead. All right, so remember, v is defined this way as its magnitude and its direction. And so if I want to look at acceleration, I can actually say, in the same way that I took velocity from a delta to a derivative, I can do the same thing with my velocity to become the acceleration, or the change in velocity to become the acceleration. This is now delta v delta t. Oops, that is not a vector, which is equal to dv dt. And if I think about it as two deltas for r, now I have a second derivative with respect to r dt. So these things are all the same. And this is how we define acceleration. Now, I'm going to pull back a little bit and think about this quantity here. dv dt, change in velocity with respect to time. Okay. So let's go ahead and look at that equation very closely because it's important. I'm going to replace v for this quantity here, v in magnitude and v hat. So if I do that, I have to take the derivative, d by dt of the quantity v magnitude times v direction. And when we take derivatives of things that are multiplied, we have to use certain rules. And this rule is just that I take the first thing and I multiply the derivative of the second thing plus the second thing times the derivative of the first thing. So d v hat dt times v plus d v dt times v hat. This is the acceleration. Okay, so let's look very closely at this. Each one of these components means something. Let's talk about what each one means. Let's say that this one talks about the speed that you're going. This is the speed of your car. Okay, so if you're in your car and you're going 5 miles per hour, that's what that would say. That's my speed. I push on the gas till I get to a certain speed, and that's what I'm doing. This tells me whether or not my car is turning. So, am I going in a straight line, or am I going around a turn? If I'm going around a turn, my velocity vector is changing. If I keep a constant speed, my velocity vector is changing if I go around a curve. If I go straight in a straight line, this is 0. But this is still a number. So this part is 0 if I don't turn. So this would be turning. Changing direction. That means that acceleration has a piece that keeps track of whether or not you're turning. So there's a component of acceleration that keeps track of how fast you're going and if you're turning. Changing your direction. Let's look at this piece. This is the direction you're going. So here's my direction, and if my direction is east, then I'm going east. This says, am I going in the same direction? Is this value a constant? It can be a constant, no problem. I can go east, but let's say I push on the gas of my car, or I hit the brakes, one or the other. They're both changes in my speed. So this is pushing on the gas. This is our familiar sense of acceleration. I'm going in a straight line in my car, and I hit the gas. That's this component of acceleration. That's our familiar one. This one may be slightly unfamiliar in the sense that one thing may stay constant, but the other thing would change. Now, the great thing about all of this is that they can change simultaneously. I could change my direction and change my speed. I could change my speed and change my and keep a constant direction. All of these add up to give us what our notion of acceleration is. GoPro, stop recording.